Good morning. This is about an instability which is driven by surface tension. Normally, surface tension is thought of as, a smoother out of instabilities, a stabilizer. This is work done with Rashmi Ramadugu. In fact, like it's part of her PhD. Prasad is her main advisor and an important collaborator in this work. I'll also be alluding to older work done with Harish Dikshit, which is relevant to this. So there are two dogmas about turbulence which people make use of all the time, and we are going to effectively argue against both these dogmas in certain situations. So when you have a vortex and turbulence is full of vortices, we are going to say that these two dogmas are not good. So here is the Navier-Stokes equation written for two fluids, one with density rho naught and the other with density rho naught plus delta rho, and with surface tension between them, like there's an interface between these two fluids, they mixed around in turbulence, and this is the equation written for them. Now, normally what people do is they check for this non-dimensional quantity called Atwood number, which is the density difference divided by the density of one of them. And if their densities are not too different, that means Atwood is much, much less than 1. What they say is that you can make this thing called the Boussinesq approximation. So, like in the Boussinesq approximation, you throw away this delta rho term and you keep only this one, which is in gravity. We've made this argument some time ago that when you have a powerful vortex, and gamma is the circulation of that vortex, in that neighborhood, when this non-dimensional number, which is like a Froude number, is order 1 or bigger, you cannot make the Boussinesq approximation. So that's one dogma. So even in low Atwood number, you can have in the vicinity of powerful vortices effects due to density gradient, which we'll talk about. The other dogma is, of course, that surface tension stabilizes, and this is because you think if you have a very wave number, that means high wavelength perturbation, then surface tension doesn't really see the curvature, except when you have like very, very short wavelength perturbations, then surface tension hates this increase in the interface length and it tries to stabilize it. So we know from long ago that this argument doesn't work in 3 dimensions. The reason is that in 3 dimensions you can actually make perturbations and reduce the net surface area, and that is the Rayleigh plateau instability, where the net surface area is reduced, and this is a surface tension driven 3D instability. But in 2 dimensions, any curvature that you put is going to increase the surface area. So how can you get an instability which is driven by surface tension in 2 dimensions? And that's the topic we're going to talk about now. So like normally in 2 dimensional turbulence, all vorticity, that means the curl of the velocity vector, is packed into these little patches which typically are close to axisymmetric or try to axisymmetrize, and their vorticity profile is like a Gaussian, and these are known as Lambosine vortices. And add to that these interfaces. So we made a building block of 2D interfacial multiphase turbulence with a Lambosine vortex and initially a flat interface like this. On either side, the two fluids have density rho 1 and rho 2. Now, in such a situation, there are two mechanisms for vortex creation, which we will talk about. So we've written the Navier-Stokes by taking its curl in terms of the vorticity equation. So this is vorticity creation, vorticity by d time. One of them is driven by surface tension, the curl of this F sigma, which is the surface tension force. And the other is driven by density gradients whenever you have the density gradient not aligned with the pressure gradient. So when that happens, you can get a vorticity creation. So these two vorticities are created only on this interface because nowhere else do you have F sigma or grad rho acting. So these are purely vorticity created on interfaces. The non-dimensional number that's going to be very important to us apart from Atwood is, of course, the Reynolds is important, but not in this context. The Weber number, which is a ratio of the inertia to the surface tension. The inertia is given by, a typical size and velocity of this vortex. So that's what UC and RC are. So now, Outside the vortex, the interface which started out, straight, because of the action of the vorticity, will curl itself up into a little spiral. We actually wrote this thing down analytically for a point vortex, and it's a ever tightening thing in time. It belongs to an Archimedean class of spirals, as we worked out. Now, what happens when you have a density contrast? Let's talk about that first. Now, you know that in the conventional situation, obviously, like whenever you have an object which I place like this, it's stable. But if I place a solid object like this, it will be unstable. It will topple, right? The same thing happens in fluids. So when you have light fluid on top of heavy fluid, density gradient is in this direction, pressure gradient is in this direction, and you get a baroclinic torque which stabilizes it. If you have heavy above light, you get the opposite. And near a vortex, we've shown that something very similar happens, because here you have now a pressure gradient in that direction, radial direction, which is the centrifugal force. And suppose your interface is like this, like slightly deviating from the circular, then grad rho cross grad P is not zero, and you get a baroclinic torque. That baroclinic torque creates vorticity on the interface. And then, like surface tension does the same thing, like it creates vorticity on the interface by this term. And that happens only when the surface tension coefficient is not zero. So if there's surface tension on the interface, we're going to fight against this dogma of stabilizing high k and doing nothing to small k, because you get this interface which is distorted by the vorticity, and therefore more vorticity is created on the interface. Now, anytime there's a vorticity, that means there's a delta function of vorticity. If I walk in this direction, there's vorticity only on the interface. So you get immediately a velocity jump. So you're getting a zero thickness infinite vorticity interface with a velocity jump. And any velocity jump results in a Kelvin-Helmholtz instability. So we're going to look for this in our flow. First, we'll run it for a single vortex like this, whose vorticity is like this and the initial interface is like this. If you have a low Atwood number and no surface tension, it passively rolls up into perfectly to a spiral outside the core, but a different shape inside the core. So we now do the analysis separately for inside the core and outside the core. So first we derive the velocity jump, and then we'll derive the instability resulting from the velocity jump. So when q, which is the radial distance squared away from the center, when it's very small, you're inside the core, and here you're outside the core. Inside the core, there's a velocity jump created primarily by surface tension, like the density jump does nothing here. There is surface tension in the numerator because Weber has it in the denominator. So delta U is proportional to the square of the time. So as time progresses, you get a quadratic increase in delta U. And in the high distance case, you get, due to both these effects, the surface tension effect and the density jump, both of them create a vorticity jump, a velocity jump. And the thing is that one of them is linear in time, the other is quadratic in time. And the density jump can be plus or minus, because heavy inside light is unstable and light inside heavy is not unstable. So like every alternate interface is unstable. Okay, so now we can actually write down the expression for the growth rate. So omega is the disturbance frequency, k is the disturbance wave number, and we impose this disturbance and we ask if it grows or decays, and growth is given by the sine of omega I. So if the imaginary part of the frequency is greater than 0, you can get instability. That means that now inside the core, this quantity which is inside the square root should be negative, only then I'll get an imaginary part. So then if this thing is negative, I get growth. And when will it be negative? This quantity is positive. This quantity represents just surface tension doing its old thing, like trying to smooth out, high K perturbations. And so this is going to be a stabilizing term. This can be a destabilizing term, but it will only destabilize if time is large enough. So like when time is greater than this, we get a Kelvin-Helmholtz instability. So here is a beautiful situation where surface tension is competing against itself, trying to stabilize and trying to destabilize. And after a certain time, its own destabilizing tendency wins, and this is our finding. So greater than this time, surface tension can actually destabilize the flow near a vortex. Let's compare this to direct numerical simulations, where you have the actual full simulation shown by these symbols and the analytical answer shown by the line. And you see that the full simulations, although there's non-linearity, there's so many assumptions we made to get this simple thing. We are doing pretty well theoretically to predict what's happening. And even the vorticity created at the interface is obeying like what we calculated. At large times, it's undergone this Kelvin-Helmholtz instability, as you see. So the vortex has effectively committed harakiri, and you're getting this breakup into very small scale vortices. Outside the core, it's a little more complicated, but even there, we can do the whole analysis and find a combination of instabilities, centrifugal Rayleigh-Taylor on alternate arms of the spiral, and also this Kelvin-Helmholtz instability due to vorticity creation. And in the intermediate region between the core and the far outside, both these mechanisms act, and there we need simulations. We can't go by analytical work. So here, without surface tension, we are showing the centrifugal Rayleigh-Taylor and spiral Kelvin-Helmholtz for a single vortex. You see this beautiful combination instability coming up. And now with surface tension, and initially without density contrast and with density contrast. This is the shape of the interface, and this is the vorticity behavior. You will see that high surface tension, namely low vorticity, generates this instability out of nowhere. And you will see that when you have an Atwood number, namely a density contrast, you get vorticity creation on the arms of the lithosphere spiral as well. And the combination effectively kills the vortex exceedingly fast, and you get left with this kind of interface and small scale vorticity. So, like in fully developed turbulence, we start with an interface which is in the shape of a flower, it doesn't matter what shape it is, and this kind of initial flow. And you see that at low surface tension, you get vorticity generation along the interfaces everywhere. This is very clearly seen. At high levels of surface tension, the vorticity is all over the place and it's peeled off from the interface. So the interface is different now and the vorticity field is different. So the two-dimensional turbulence picture has changed, and as you increase surface tension, you'll see that there is more and more and more energy in the small scale. So this is the standard energy spectrum in turbulence. And I will now summarize with this result showing that we've actually shown that surface tension can destabilize a generic interface in two-dimensional turbulence. Thanks for your attention.